Alright, so welcome everybody. We're doing proposition 12 today. Alright, so let me draw the picture first. In obtuse angled triangles, such as ABC here, the square on the side subtending the obtuse angle, so remember subtending means sort of opposite, is greater than the squares on the other two sides. By an amount that's kind of very awkward to say in English. By twice the rectangle contained by one of the sides about the obtuse angle, namely that on which the perpendicular falls, and the straight line cut off outside by the perpendicular towards the obtuse angle. Okay, so the perpendicular means, yeah, it's sort of like trying to say in language what happens in the picture, and it doesn't really work. So, okay, one of the sides, so if you extend the angle, if you extend the side AC, you'll get a line to which you can draw a perpendicular from B, right? And so that's what it's referring to when it says it's greater than the squares on the other two sides by twice the rectangle, and I'm just going to use the letters in the diagram on, so this is D, CAAD. Okay, so that's a pretty simple statement. Proof. I suppose I did not think about why when you I guess we could also do it out here, right? And have dropped a perpendicular. They must, yeah, that has to work, right, from either side. Yeah, so just pick one of them. Proof. The square on DC equals the square. So what I'm saying here is a plus b squared is a squared plus 2ab plus b squared, where this is a and this is b. This was proposition 4 of this book. The square on DC is equal to the squares on CA, AD, and twice the rectangle on CAAD. That's, as I said, but the square, sorry, so add the square on DB to each. So the squares on CDDB are equal to the squares on CA AD dB. But the square on CB is equal to CD squared plus DB squared by Pythagoras. So, and AB squared is AD squared plus BD squared. So coming back to this being equal, the squares on those being equal to the squares on those, we have CB squared is equal to CA squared plus AB squared. Okay, so what's the logic here? So we start with this, the square on DC gotten lost. Add the square dB to each. The squares on CD, dB are equal to the squares on all of that. Okay. But that sum of squares is CB squared, and this sum of squares is AB squared. So what I've gotten out of that is CB squared is equal to CA squared plus AB squared, right? Yep. Wait, and twice the rectangle contained by CAAD. Oh yeah, okay. Yeah, okay, so yeah, that's right. So from the first statement. You all with me?
I am.
Yeah. Okay. So, maybe I'll just go through it again. So the square on DC equals the square on CA and AD plus twice the rectangle, and then we do something with the square on, so the square on CA plus the square on AD plus the square on DB is the square on DC plus the square on DB, and then that gives us the right hand side. Okay, so now basically that's it. That's the claim, right? So the square on the side subtending the obtuse angle is greater than the squares on the other two sides. That's CA. Oh, sorry. No. Yeah, that's right. Squares on the other two sides by twice the rectangle on CAAD. Okay, so that's the end. Let me point out how we would write this, and so what this sort of is from our point of view. So if I call that theta, and this is pi minus theta. So if I call this, oops, I call this B here. Then that makes this side here, well, B cosine pi minus theta which is minus b cosine theta, theta being obtuse. So in algebraic form, this says, so I'll call this C. So this says C squared is equal to A squared plus B squared plus 2CAAD, so that's 2A and AD. Oh, no, this is still wrong, right? Oh, no, yeah, okay. AD is minus B cosine theta. Okay, so that's A squared plus B squared minus 2AB cosine theta, which is, of course, the law of cosines. Yeah, which usually I would prove with inner products, but I guess it's kind of the same argument ultimately. All right, any questions? I think we have time for proposition 13, Kenneth.
Yeah, I think 13 is almost the same as this. It's just with an acute angle. And I think we can. Oh, I should join as a speaker first. Oh, yeah. Yeah, so 13 is very similar to 12 because it's the other cosine rule where the angle is acute instead of obtuse. I'm just going to move over a bit. And the most difficult part of this proposition is parsing the English in the statement. The proof is going to go pretty similarly to 12, and so I'll do this probably pretty quickly since we basically just saw the argument. So proposition 13, I'm going to Dandy draw the picture first because it'll make it a little bit easier to state the proposition. So we have a triangle which now has an acute angle. It's not a right angle triangle, it's just any old triangle. And the acute angle is going to be the one at A, right? So I'm just going to mark this angle as the acute angle that we want to refer to. So in an acute angle triangle, the square on the side subtending A subtending A, and that would be BC squared, is equal to, or actually is less than, in this case, less than. We're not allowed to subtract, I guess, but we're kind of doing it, right, by this language. Less than the sum of the square on the other two sides. And that would be AB squared plus AC squared, okay, by a certain amount, and that amount is the big mouthful, which I'm just gonna write in symbols. By twice the let me make sure I get this right, is 2BC times BD, and I realized that just after I said this I haven't defined what D is, so let's define it. Going to drop a perpendicular from A to BC, right? So that's a right angle here, and we know we can do this perpendicular line using proposition 1.12. Allows us to drop perpendiculars, and the intersection of this perpendicular line with BC is what we call D. Okay, so BC and BD now makes sense. So in the text they say the rectangle formed from BC and BD, and then they have to do some linguistics to explain what BD is, but we're just going to use the symbol. And we can also see here why we had these propositions earlier with kind of strange algebraic identities that we thought at least were a little bit superfluous, right? Why would Euclid do this? And I guess we're seeing the application now, right? So we're gonna refer back to proposition 2.7. So proposition 2.7. I think in the previous proposition, what Dan just did, we're referring to proposition 2.4. So 2.7 is used to prove this case. 2.4 is used to prove the other case. And so I know we're not going to remember what it says, so I'm just going to mark the lengths here. So there's A and there's B. And proposition 2.7 is really an identity on the quantities A and B, or the squares of them. And all you're given is a line and some random point in the middle. In this case, the line is BC. The random point in the middle is D. It splits up into two possibly unequal parts, A and B. And the identity that you get from the proposition 2.7 is that A plus B all squared plus A squared is equal to 2A plus B times A plus B squared, which we're going to just rewrite in terms of the labels that we've put down for this diagram. So A plus B all squared is BC squared. That's the whole length of the line. BD is A. A is BD. Well, BD is A. BD squared. All right, and that's equal to 2. And you can already see where the twice comes from because there's a 2 in this identity. BC and A was BD. So we're really just substituting the labels into this algebraic equation, kind of doing things backwards to what we would usually do. So DC squared, right? And the only kind of trick here that completes the proof is that we add dA squared to both sides. Okay, so we're gonna just do that, plus dA squared plus dA squared. Remember, dA squared is this length here. It's that vertical line that we, the perpendicular line that we drew from A to BC. And by Pythagoras, we can see that these quantities are actually just equal to the square on the hypotenuse. And so we can just sub those in. So by proposition 1.47, right, we get that BD squared plus DA squared is equal to AB squared. And on the other triangle, the other right angle triangle, DC squared, undo, wrote a little too fast, DC squared plus DA squared is equal to AC squared, right? So we put those in into here. So this becomes AB squared. This becomes AC squared. And I think this is essentially it, because if you go back to the statement, right, we've got did I do this right? AB plus BC, right, on one side, that's this. And we've got like AC on the other. Did I do this wrong?
I'm a bit confused, yeah.
Hang on. I think I've done this a little bit. I've missed something. So let me just get this right. So DC squared, we're adding dA to both sides. We get ABAC squared. No, hang on.
I think it's right. It's just not what you
Slow down a
stated
bit.
in
So-
the proposition. The proof seems right.
The proof seems right. Probably the labels are just a bit off. We can.
Yeah.
So the proposition, other two sides. Okay, yeah. AB plus AC squared.
I think you mean
is the
BC
other two
squared.
就这一个你肯定至少比一个大学生家教要好。
Oh, yeah, I did it. Yeah, sorry. the straight subtending is a BC, and the sum on the other two sides.
It still is a mismatch
Yeah,
between the
this is some pretty
statement.
confused myself. It's actually a. Yeah, sorry, it's not the other two sides. I did this wrong. That's not quite right. So we want square on the side containing is actually
Yeah,
AB squared.
you drew
plus
the
BC
angle at
squared.
A, but actually the angle, if you're following the notation in Euclid, the angle is at B. So there's an acute angle at B,
Oh,
and then
yeah.
the subtending side is AC
There you
squared,
go.
which then matches the rest of the proof. Yeah.
Ah, thanks. Also, now we have to kind of replace this. The one subtending B is now AC. Yeah, you're right. Yeah, this is now AC. And then the other two sides, that's correct. But then, well, that's not correct. This is now
That's right. So it's
the
AB
other two.
squared and
Whatever's in the
BC
formula.
squared. That's right. Yeah, AB squared and BC squared.
AB squared plus BC squared. Oh, so I guess that was that one error. Thanks. Okay, so we get rid of this. Oh, that's okay. It is the other two sides, I
Yep.
guess.
Yeah, as you say, it's basically the same. It's just whether that vertical line is inside or outside.
Yeah. So this is a lesson in how notation is really nice. Using natural language, we wrap ourselves into these confusing kind of loops. Yeah.
Well,
And so now everything matches up. Cool.
yeah, it's interesting that the natural language is kind of more referential, right? It sort of refers always to earlier things in the English, whereas the notation is kind of more absolute, right? You give more names to things, and that has a proliferation of symbols, but in some sense, it's. I wonder if they actually just found it easier to read the other way, and we're just used to this more absolute. I mean, maybe they would say we have too many letters or something, but still, these diagrams do have a lot of
I
letters.
don't know. Like, there's a difference between using hash tables versus lists, right? Like, if you're writing code, you would never just refer to indices and be like, oh, not even lists that you can refer to the index. You got to go back. You got to be like the previous one compared to the previous one plus the next one, right? That gets super confusing. Whereas if you just label everything, I don't know. They didn't code back then. Certainly, I find it easier to have labels, right?
Yeah, this is about as close as it gets to coding in ancient Greece, I guess.
Yeah, right.
All right, I guess that's
So
it.
this is the end of, like, there's one more proposition in book 2, and that's the end, right?
Yeah.
But this seems to be the point of book 2, right? We used a lot of the previous identities, and we've gotten these, pretty useful. I mean, we've all used this cosine rule, right? Maybe not recently, but at some point we used it.
Yeah, I think this is it's kind of easy in the end. I feel like book 2 didn't really have anything as involved as the proof of the Pythagorean theorem. It all felt fairly routine, but this is a good result. I'm quite interested. I hadn't really paid attention to proposition 14, which we'll do next time. It's a bit longer, and it sort of involves circles again, which we haven't seen for a while. And it seems like this is actually the foundation of a truly general notion of area, because it says that
Nice.
if we're given a rectilineal figure like A on the left, we can construct a square with the same area. So that seems kind of interesting. We've often discussed how area is, not just a number for Euclid. It's kind of a more intricate concept. So yeah, that's next time.
Yeah. Cool. Awesome.
Yeah, thanks everyone.